Yeah. So, but the number of dimensions that they get, oh, and time they call a dimension, and then of course the other uh, six, is it six? Yeah, one, two, three, four, six are wrapped up in some kind of dimension, right? The other dimensions are just wrapped up or rolled up somewhere. Yeah, not a good theory. I mean, it's, I don't know why. Depending on how you set, that's what I said before. Depending on how you set up your mathematics, right? I mean, you could pretty much get anything. There's nothing special about the number 10. There's nothing special about the number 11. It's the assumptions you used and what you put in there to make the equations work, and that's the kind of stuff you'll end up with. So you can make the math work. The question is, has it any meaning? And I think I talked about this in my last video, or the one before this, right? Just because you can make a mathematical equation doesn't mean it has anything to do with reality, okay? Just because you can write a mathematical equation doesn't mean it has anything to do with the true understanding of how the universe works. So you have to be careful. So if, like I said before, if the concept is correct, the math will follow. It doesn't follow, if you make the math, the concept has to be correct. That doesn't necessarily work. All right, many dimensions. Well, this is one, so, I was going to say what I said in my other video, the previous one, viewpoints. I said you might as well take go to a large chicken farm, like they might have at Purdue, take a piece of paper or a big roll of paper, roll it out, and put numbers on that paper, right? Run to whatever the numbers are, and walk away. And and when you come back, the chickens would have shit on it, and the number that has the greatest amount of shit on it is the number of dimensions in our universe. That's pretty much string theory, right? I mean, chickens shitting on a number line is pretty much equal to string theory, right? So anyway, I won't say more about that. You got the idea. Colossal collision. When I wrote a paper about breaking the light barrier, adding velocities beyond the speed of light, it was actually to a conference in Russia, and it was elected as a poster paper. I didn't go, but it was published later by the, you can still get it, on the Institute for Electrical and Electronic Engineers, IEEE, right? So you can still get it. I actually sent some other papers, and one of the papers I sent there, which they said was just beyond the scope of the conference, was something called the colossal collision. And we know that there is always collisions happening within the universe, and certainly in the very early stages of the universe, right? Look at the moon. You can see the craters. On Earth, there's plenty of craters, but they just might, Yucatan Peninsula, right? They kind of disappear underneath the water, or the land has covered it in. Some haven't, but you can still see the some remnants of the collisions. And then the Shoemaker Levy, let me see what year that was. 1994. It's when was it an asteroid or a comet broke up, and all the pieces of that comet went into Jupiter, and they took pictures of it, and you could see the holes that it made, or when it went into the actual atmosphere, and you could see the points of entry, and it's sort of the splash or the breaking of the surface there. It's pretty interesting. So collisions happen all the time. Well, I mean, it might be possible, I thought. What happens if I don't need a singularity? We don't know how the universe starts, but from our perspective, what happens if there are two, gigantic balls of matter, and if space is infinite, they happen to collide? So it's like two giant galaxies, but maybe not quite that, that got together or that hit each other. and expanded, and that's what caused the universe that we see. Possible. We know that if one galaxy goes to another galaxy, it's not like everything will collide because it's mostly space. So what you'll see is a lot of just sort of passing through and changing their trajectory, and other things will collide and explode or whatever. So I'm just thinking, well, it's very possible that you had some type of collision like that, and that's what we see. You'd still get the cosmic microwave radiation, right? And so it's a possibility, I put it that way, to get in. It's a possibility because I don't really think much of the singularity. It's just Einstein's field equations extrapolated backwards, and you end up with that, but I don't think it's theoretically relative. Okay, so that's something else. I never published it anywhere, so nobody's going to publish it anyway, right? So what else do we got? Okay, so I think I have more about this later, right? I have to look at my own writing because I don't remember everything I wrote. These are done on a budget, by the way, of 0. So I just let the camera run and I just do the best I can. So they're a little raw, but hopefully you'll get the idea of what I'm doing. The science is important. I'm not, but the science is important. That's what I want to get over to people. So if you look at this, space is a necessary existing condition for matter. In other words, look at a supernova, right? You have to have space in order for it to explode, expand, start to burn, however you want to look at it, right? Space is a pre-existing necessary condition. It has to be there. You don't unfurl space at the same time as you unfurl, like you can unfurl time, and it just sort of spreads out. No, and it creates its own space at its own time, and it doesn't happen that way, right? Space, think of any explosion that you can think of, even the Hiroshima explosion, or the Hiroshima bomb dropped over Hiroshima, Japan, sorry. And, they can trace it back, basically, of what height it exploded, where it exploded, and so forth. But it had to have space. Any explosion that we see, even in the universe, has to have space, right? So if you go back to the singularity kind of idea, there was no space. I think that's pretty untenable as a theory or a hypothesis, right? I think space was there, and I don't know, something happened. I mean, the other thing with the colossal collision is that it seems Andromeda Galaxy and the Milky Way are sort of coming together, right? But if it was a straight explosion from one object, whatever size it was, all part, whoop, whoa, getting excited here. If they were to come together, you couldn't get that with one explosion because it just radially goes out. So a lot of objects that are sort of coming together or coming in the opposite direction from expansion, like Hubble's expansion going out, you have to figure out why that's happening. I'm not sure we have yet, but it's a question. All right, so that is, space is a necessary pre-existing condition for matter to explode, right? You get nothing from nothing. It has to be something. Something had to exist in order for that to happen, okay? Blumdahl's postulate. Oh yeah, that's Blumdahl's postulate, right? Space is a necessary condition. Again, I have to bend over because I don't remember what I wrote here. No space-time, a la the general theory of relativity. No space-time, yeah, by the general relativity, space is independent of matter and objects linked by gravity. In other words, what's out there is linked by gravity, right? It's not like there's space-time, what you think like rippling space-time. It doesn't exist. I mean, that's a an idea out of the general theory, but they think they've discovered space gravitational waves, and they didn't, because the LIGO experiment that they did was a complete flop. So they've uncovered nothing about gravitational waves. At this point, it's zero. So yes, no space-time a la the general theory. Space is independent. Matter objects are linked by gravity. Since space cannot be compressed or displaced, a cosmic seed burst a cosmic seed burst forth into not with space. Oh, okay. Here's what I'm getting at. That's a little rough for writing, but that's okay. Right. What happens is not this idea about from a singularity, everything like, where is the singularity? Well, you can't answer that question. You know, well, nobody asked. It takes no geographical space. I mean, right? So it's there. And what I'm saying is, you can't have that. Space has to be pre-existing, and what happens is matter, whatever it is, sort of explodes into space. It's not like a blanket. You know, the universe is not like a blanket where you just kind of unfold it a little bit and the sides and everything, and that's not what's happening. It explodes like any explosion, like a supernova to a firecracker to a firework to a pipe bomb, right? The principle is generally the same, even if the physics isn't, right? So matter, time and space are all independent of each other. There is no space-time in the Minkowski view. There is no space-time in the general theory Einstein's view, right? There is no melding together of space and time. Why? Time does not exist, right? Other people have said this. I don't think I'm the first to say that. You know, in absolute time, it doesn't happen. What we know is relative time, like it's 3 o'clock in the afternoon or something, but not absolute because it doesn't exist. How can you put together three-dimensional space, which does exist, with a concept that doesn't exist? You can't. So we back out, go all over again, and we're back to sort of Newton's view, right? There's space, there's objects, there's gravity, right? There is no melding together. So in the LIGO experiment, they have no gravitons. They have nothing to do with gravitons, right? No one knows about that. Second, they have space-time, but if you have space-time, as I've always said, you have to define the material reality of the composition of space-time. If it bends, it can't be nothing, right? I mean, that's a third-grade science concept. You can't hold nothingness, right, or a vacuum or emptiness, right? You can't do that. So there is no warping, curving of space and time. It doesn't exist. So the fabric of space-time doesn't exist. So 0 for 2, and then when they